So this question is very similar to the question that was on the exam. However, here we only have injective, whereas before we had that it was isomorphic. So here we're only allowed to go one way. So it's an if and only if statement. So I can go both ways, and I can either assume linearly independent or I can assume linearly dependent for both directions. I'm going to go linearly dependent. And in the forward direction, I'm going to assume set TV1 through TVN is linearly dependent. With it being linearly dependent, there exists a linear combination I going from 1 to n of AI T VI equaling 0 such that at least one AI does not equal 0. Now, this implies that T of the sum of I equals 1 to n of AI VI equals 0 using properties of linear transformations, which implies the sum I equals 1 n AI VI is in the kernel T as T is injective. Kernel of T is just the set containing the 0 vector, which implies that the sum I equals 1 to n of A1 AI VI equals 0, which implies with at least 1 AI not equal to 0, which implies that the set V1 through Vn is not, or is linearly dependent. Now, for the reverse direction, assume set V1 through Vn is linearly dependent, then there exists sum of I equaling 1 to n of AI VI equals 0 with at least 1 AI not equal to 0, applying T to both sides gives T the sum of I equals 1 to n of AI VI equals T of 0, which implies that T, the sum I equals 1 to n of AI T VI equals T of 0, which implies that the sum I equals 1 to n of AI T VI equals 0 with at least 1 AI not equaling 0. Thus, the set T V1 through TN is not, or is linearly dependent. So now I'm going to do B7 and B8. So in B7, we want to show that the derivative operator applied to the set of all real polynomials is surjective. What this means is remember, the derivative operator maps the set of polynomials, P polynomials defined over real numbers to the set of polynomials defined over real numbers. So let f of x be in PR of x, then f of x equals the sum of I equals 1, 0 to n, with a n, ai, x to the I. And we want to show that there always exists some polynomial that gets mapped to this. I'll let g of x equal the sum of I equaling 1 to n of a I over I going from 1 to n plus 1 of ai minus 1 over I x to the I. Let's change this to n, I going from 0 to n of ai over I plus 1, x to the I plus 1. And if we apply the derivative to g of x, we get the sum, the derivative applied to the sum of I equaling 0 to n, the ai over I plus 1, x to the I plus 1, which equals I plus 1, the sum of I equaling 0 to n of the derivative applied to ai for I plus 1, x to the I plus 1, which equals the sum of I equaling 0 to n of I plus 1 over I plus 1 times ai x to the I, which equals the sum of I equaling 0 to n a I x to the I, which equals f of x. Thus, for all f of x in PR, for all polynomials, for all real polynomials, there exists a g of x in R, or in the set of real polynomials, such that derivative of g of x equals f of x. Thus, D is surjective. Awesome. So we have a surjective operator. Okay. Now what we're going to be looking at is we're going to be looking at showing that we have a linear transformation from V to V, and we're going to show that the eigenspace is T-invariant. What T-invariant means is that if V is in E lambda, then T of V also in E lambda. To show this, we have a let V be in E lambda, then T of V equals lambda V. Well, T, we want to show that T of lambda V equals lambda V, i.e. lambda V is in lambda. Well, T of lambda v equals lambda T v equals lambda times lambda v. Therefore, lambda v is in E lambda. And we're done.